For lab this week, we're going to be dealing with real gases and comparing them to ideal gases. How do they behave? Is there some way that we can generalize how real gases behave? So we'll be looking at the compression factor and also using reduced variables. What makes real gases different from perfect gases? Well, we've got our postulates of the kinetic molecular theory here that tell us that the gas is made up of atoms in ceaseless random motion. That's going to hold pretty well. The size of the gas particles is negligible in comparison to the space between them. That's something that is invalid for real gases. And that collisions are elastic and molecules do not have any other interactions with each other. And we know that that's not true either if we think about intermolecular forces. If you think about two gas molecules or gas particles far apart from each other, like a perfect gas would be in the kinetic molecular theory, you'd be out here in this region of a distance between particles versus the volume. Okay, so sort of what we've got here is the like a relative volume, a volume versus ideal volume or perfect volume. And if you're way out here where your distance between particles is super far apart and they're not going to see each other, not going to interact, then this is where you've got your perfect gases. Okay? As they get closer together, as you start to compress that gas, you increase the pressure. Those are going to become closer to each other, and we know that intermolecular forces will appear. And those intermolecular forces are going to pull particles together, and your volume of a real gas is going to be less than the volume of a perfect gas. If you keep applying pressure and you force those atoms or molecules or particles close enough together, they're going to start to repel each other because they can't physically be in the same space. And the perfect gas law does not allow for that in any way. So you know that if you bring two atoms or two molecules too close to each other, then the nuclei are going to start repelling each other. So now we're going to have this repulsive force that's going to push particles apart, and the volume that the gas takes up is going to be greater than the volume that a perfect gas would predict. And so we use the compression factor to compare the behavior of real gases to that of perfect gases. So the compression factor Z is the ratio of the molar volume of a real gas over the molar volume of a perfect gas. So out here, if you have a perfect gas, then Z is going to equal 1. So if your real gas actually does behave as a perfect gas, then you have the same thing here. So you have 1, and that's this red dotted line is indicated here on this compression factor versus pressure bar. Now, if the pressure is super low, approaching zero pressure, then we know that those molecules or particles are very, very far apart from each other, and that's the limit in which you're going to have a perfect gas. Those particles are not going to interact with each other. As you start to bring them together by increasing the pressure, so as you increase the pressure, those intermolecular attractive forces are going to bring those particles closer to each other than the perfect gas law would predict. So we're going to have a compression factor that's less than 1. As soon as you increase the pressure high enough beyond the point where the molecules don't want to be next to each other, the nuclei of the two molecules are going to repel each other, and they're going to start to push the particles apart. They're going to take up more volume than the perfect gas would predict, and so your Z is going to be greater than 1. So this is generally how gases behave. These particular numbers are for methane. And if we look at a bunch of different gases, then you can see that they kind of all behave differently. And in lab, I'll be asking you some questions about like, well, why do you think that helium just goes straight up and versus methane that dips down a bit, etc. What is causing these different behaviors? We can also talk about perhaps all of these gases would behave the same if they were under the right conditions. So is there a way that we can generalize how real gases behave And we do that using reduced variables. So reduced variables, as you can see here, we see the reduced pressure, the reduced temperature, the reduced volume. Okay, those are given as the actual pressure, the actual temperature, and the actual molar volume of the gas. Each one of those things divided by their critical pressure, or their critical temperature, or their critical volume. Just to remind you what these variables are, the critical variables are the ones that occur here in the phase diagram. So this is your typical phase diagram. You've got a solid, liquid, vapor, or gas. And out here is the critical point, and beyond this point out here we have a supercritical fluid, where we no longer have a sharp distinction between a liquid and a gas. Now it's just a continuously variable substance, right, that you can change, you can compress, and it just acts as a fluid. So that critical temperature, pressure, and volume that's associated with that point, that's different for every gas, every substance. But when we use reduced variables, now we're putting all of the gases onto a relative scale relative to their critical pressure, critical temperature, and critical volume. The principle of corresponding states is an approximation that says real gases at the same reduced variables will exert the same reduced pressure. So we're going to be exploring that in lab. We're going to use the van der Waals equation of state for real gases to plot that compression factor as a function of pressure. We're going to explore how that changes for many different real gases and how it changes as a function of temperature as well. We're going to determine the limits where real gases behave as perfect gases. And then we're going to use reduced variables to verify the principle of corresponding states. Now, all this work is going to be done in Excel, and I'll be walking you through a lot of the more complicated functions. We're going to be using goal-seek and some other things, but you will have 2 weeks to walk through this in lab.